Something is happening at the edge of the observable universe that has no clean explanation yet. Stars are vanishing, not burning out, not exploding in the violent, predictable way that massive stars are supposed to end, not fading slowly the way smaller ones do over billions of years, just gone, present in one image, absent in the next, no flash, no remnant, no signal of any kind left behind to explain the transition. And the machine that keeps catching them was not even built to look for this. Stick around, because I am about to walk you through what researchers are actually finding. Why the leading explanations all have something that does not quite fit, and why this particular mystery is unlike almost anything else currently sitting inside an open scientific file. Hit subscribe now, because this channel covers real discoveries grounded in published research, and you do not want to miss where this one goes next. Let's start with what we actually mean when we say a star disappears, because the word disappears sounds dramatic, and in this case, the reality is somehow more unsettling than the drama. When a massive star reaches the end of its life, the standard model of stellar physics gives it a very specific exit. The core collapses and the outer layers rebound. The resulting explosion, a supernova, briefly releases more energy than the sun will produce across its entire 10 billion year lifetime. It outshines entire galaxies. It leaves behind a neutron star or a black hole, surrounded by an expanding cloud of glowing debris that can remain visible for thousands of years. You cannot miss a supernova. Every major sky survey in history has been catching them regularly. They are the punctuation marks of the universe. Loud and bright and impossible to ignore. A failed supernova, by contrast, does something that the physics also technically permits, but that nobody had directly confirmed until very recently. The core collapses, but instead of triggering a rebound explosion, the entire mass of the star crosses the threshold into a black hole almost instantaneously. No blast, no expanding shell, no neutron star remnant. The light from the star's outer layers, still traveling toward us in a moment of collapse, simply stops arriving. One frame of data, there is a star. The next frame, there is a gap where that star used to be. Nothing else? No afterglow? No debris cloud? Just an absence in a place where something used to exist? For decades, this was a theoretical prediction sitting inside stellar physics models with no confirmed real-world example attached to it. The reason it was so hard to catch, that was not because the event was rare. It was because of what you have to look for. Every other major astronomical discovery involves finding something that is present, a new object, a new signal, a new structure. Catching a failed supernova means finding something that is no longer there. In a universe containing an estimated 2 trillion galaxies, each holding hundreds of billions of stars, scanning for specific absences is an almost impossibly difficult task, with traditional instruments built around capturing what exists rather than cataloging what has stopped existing. That limitation began to change in a serious way starting in 2025, when the Vera C Rubin Observatory in Chile began its early observation runs. And what has been returning ever since has quietly shifted the conversation in ways that most people outside of professional astronomy have not yet heard about. Here is what makes Rubin fundamentally different from every other sky survey ever built, in a way that matters specifically for this kind of discovery. Every telescope that came before it operated on a single basic model to point at a region of sky, capture an image, move on. Even the most sophisticated surveys were built around accumulating individual snapshots, each one standing alone, with comparisons between images requiring researchers to manually cross-reference datasets collected months or years apart under different conditions. Finding a star that had vanished inside that kind of system required someone to already suspect something was wrong, to already know roughly where to look, and to already have a clean historical baseline image to compare against. It was the equivalent of trying to notice that a single specific grain of sand had gone missing from a beach by walking the shoreline once a year with a magnifying glass. Rubin was designed around an entirely different principle. Every 3 to 4 nights, it photographs the entire visible southern sky, not selected regions, not priority targets, all of it. And then automatically it compares every new image to every previous image of the same patch of sky, flagging anything that has changed, a dot that brightened, a dot that didn't, a dot that moved, and a dot that is no longer there at all. The system generates approximately 7 million of these alerts every single night, each one representing a detected change in the sky, processed and distributed to research teams around the world in something close to real time. What this means in practice for the specific question of vanishing stars is that Rubin is doing something no previous instrument could do. It is building a continuous, high-resolution memory of the sky, updated every few nights, precise enough to notice when an individual star in a distant galaxy simply stops appearing. Not after someone thinks to go looking for it. Automatically, systematically, every few nights across the entire southern sky simultaneously. The results coming back from that system have been, depending on who you ask, either thrilling or deeply uncomfortable, probably both. If you're the kind of person who finds this kind of story genuinely compelling rather than just abstractly interesting, go ahead and drop a like right now, because it directly helps this kind of research-grounded content reach more people who want it explained without the exaggeration. Let's talk about what the data is actually showing, because there are several different categories of stellar disappearance turning up inside Rubin's observations, and they do not all have the same explanation. That is part of what makes this particular dataset so difficult to process cleanly. The first category is the one researchers were most prepared for: failed supernovae, the theoretical prediction that has been sitting in the models for decades, waiting for an instrument sensitive enough to catch it in real time. Rubin's images go roughly 100 times fainter than earlier sky surveys. That sensitivity matters enormously here, because the stars most likely to undergo failed collapses are among the most luminous objects in any galaxy, massive enough that their final light should be detectable across enormous distances even with a modest instrument. At Rubin's sensitivity, those stars are visible across a significant fraction of the observable universe. When one of them simply stops appearing between one observation run and the next, the system flags it. Researchers then work backward through the archival data to confirm that the object was genuinely present in previous images and that what they are seeing is a real absence rather than an artifact of the imaging process. The first serious candidate to come out of this pipeline was identified in the Andromeda Galaxy, roughly 2.5 million light-years from Earth, and reported in peer-reviewed research published in the journal Science in early 2026. A massive star in that galaxy's outer disk simply stopped appearing in Rubin's data, with no corresponding flash, no detectable shockwave, no radio or X-ray signal of any kind from the location. Researchers working with Stephen Smart at the University of Oxford, who leads one of the data analysis pipelines connected to Rubin's alert system, described the candidate as consistent with a direct collapse event. Not confirmed as one yet, because confirmation requires ruling out a long list of alternative explanations, but consistent in a way that previous data never cleanly was. That case is still under investigation, but it was not the last one to show up. Within the first several months of Rubin's early survey operation, researchers working through the alert pipeline have flagged multiple additional candidate events distributed across galaxies ranging from a few million to several hundred million light-years away, each one sharing the same basic signature: a massive, luminous star present in historical imaging, absent from recent observations, no detected signal at any wavelength to explain the transition. Now, here is where the story becomes genuinely complicated, because not all of the disappearances fit the failed supernova model, and the ones that do not are, in some ways, more difficult to explain. A subset of the vanishing stars identified in Rubin's data are not the kind of stars that stellar physics predicts should undergo direct collapse. They are not massive enough. They are not at the right stage of their evolutionary cycle. They are, in a few cases, stars that look remarkably similar to our own sun in terms of mass and age, sitting in distant galaxies at the far edge of what Rubin's sensitivity can reliably detect. And they are disappearing. Stay with me here, because this is where it gets genuinely strange. There are a handful of conventional explanations worth working through before arriving at the ones that do not sit comfortably inside existing frameworks. The first and most straightforward is dust obscuration. A star can appear to vanish from optical imaging if a dense cloud of dust or gas moves between it and our line of sight, blocking the visible light it produces while potentially still radiating detectable infrared emission. This is a known phenomenon. It happens. In some fraction of cases, it is almost certainly the explanation for a reported disappearance, but it does not explain cases where the star is also absent in infrared wavelengths, which several of the flagged candidates are. And it does not explain the pattern of how these events are distributed across different galaxy types and stellar populations in ways that do not match what you would expect from a dust-driven effect. The second conventional explanation is tidal disruption combined with extreme variability. Some classes of variable stars can dim so dramatically over specific periods that they effectively disappear from imaging, sensitive only to their baseline brightness. This too is a real effect. It too explains some fraction of what gets flagged. It does not explain the ones where the dimming is permanent across observation windows spanning more than a year, which is long enough that even the most extreme known variable stars would be expected to show some return of brightness. The third explanation is the one that some researchers are beginning to take most seriously as a category distinct from failed supernovae, and it connects to something that has been a growing source of tension inside stellar physics for roughly a decade. The tension between what the models say stars in certain mass ranges should do at the end of their lives and what real observations of actual stellar populations in distant galaxies are beginning to suggest they are actually doing. Here's the background you need to understand why that tension exists. Stellar evolution models are built from physics that is extremely well tested in certain regimes and considerably less well tested in others. The behavior of stars in the mass range between about 8 and 40 times the mass of our Sun is reasonably well understood, at least in broad terms. Below that range, and above it, the models involve assumptions and approximations that have been difficult to test directly because the observational data has always been limited by instrument sensitivity. Rubin is now providing data in a quantity and at a sensitivity level that is beginning to stress test those models in real time, and in at least some cases, what the data is returning does not match what the models predict. Specifically, there is a growing body of flagged events involving stars in mass ranges where the expected outcome is not a dramatic collapse, but rather a comparatively quiet transition into a white dwarf or a neutron star over an extended period. Of time? Stars that, according to the models, should not be capable of direct collapse because they are not massive enough to generate the conditions required, and yet they are disappearing cleanly, completely without the extended fading or the thermal signature that the expected transition should produce. Researchers working on this data are careful with their language. They are not claiming that the models are wrong, they are saying that the data is posing questions that the models, as currently constructed, do not have clean answers for. That is a scientifically precise and appropriate thing to say. It is also, if you sit with it for a moment, a remarkable thing to be saying in 2026 about a process as fundamental as how stars die. Now, step back from the individual data points for a moment and consider what the pattern itself is telling us. Rubin's full Southern Sky survey has been running at or near full capacity for less than a year as of this writing. In that time, it has generated enough stellar disappearance candidates to constitute what researchers are beginning to describe as a statistically meaningful sample, meaning enough events distributed across enough different galaxies and stellar populations that the distribution of events itself is starting to carry information. Not just about individual stars, about the rate at which this kind of event occurs across the universe as a whole. The preliminary rate estimates, still early and still subject to significant revision as the sample grows, are suggesting that direct collapse events may be happening somewhere in the observable universe far more frequently than the models predicted before Rubin started watching. The exact numbers are still being worked out and will be for years, but the rough implication is that if you take all the massive stars in all the galaxies Rubin can observe and look at how often one of them simply disappears rather than exploding, the fraction doing so quietly may be substantially larger than anyone expected. Think about what that means if it holds up. Every time a massive star collapses directly into a black hole without exploding, it adds a black hole to the universe without any of the announcement that a supernova would produce. No light burst detectable across millions of light years, no expanding debris cloud, no observable evidence that the black hole now exists at all, unless something eventually falls into it or interacts with it. In a detectable way, if the rate of direct collapse is genuinely higher than the models predicted, then the actual population of black holes distributed throughout the universe may be substantially larger than any estimate. Built from supernova rates would suggest there could be more black holes in the local universe alone than there are stars currently visible to every telescope on Earth combined, and most of them formed without anyone ever noticing. Now picture for just a moment what it would look like to stand in one of those distant galaxies and watch this happen. You would see nothing. That is the entire point in the direction of a star that had existed for perhaps 10 million years. Burning at temperatures that dwarf anything our sun produces, there would simply be a patch of darkness where there had not been one before. No flash, no ripple visible to the naked eye, no shockwave reaching out across the surrounding gas clouds. The transition from star to black hole would be, for any observer in that galaxy, completely invisible. It would be as if the star had been erased rather than destroyed. The only way to know it happened at all is to have been watching continuously, with sensitive enough instruments, at precisely the right moment of cosmic time, and across almost all of human history, we have had neither the instruments nor the cadence of observation to catch it. We do now, and what we are catching is making the already strange landscape of stellar physics considerably stranger. There is one more layer to this story that has not been widely reported outside of technical literature, and it is the part that tends to sit with people longest after they hear it. Rubin is not the only source of data on this phenomenon. In parallel with the disappearance events being flagged from optical survey data, researchers working with the James Webb Space Telescope have been conducting targeted follow-up observations on selected PRAD candidates using Webb's infrared sensitivity to probe what is happening in locations where optical light has stopped arriving. In several cases, those observations have returned something unexpected. Not nothing, which would be consistent with a simple direct collapse, and not the infrared excess you would expect from dust obscuration, which would look like a star whose visible light is being absorbed and re-radiated at longer wavelengths. Instead, a faint, unresolved infrared signal that does not match the spectral profile of any of the standard explanations, too faint and too spectrally unusual to be the star itself, too localized to be a diffuse background source, not consistent with any known class of stellar remnant. The researchers who have studied these particular cases are being extremely careful not to overstate what the signal represents. They are not claiming it is evidence of anything exotic. What they are saying is that it does not fit cleanly. Inside any of the conventional bins, it requires more data, it requires follow-up at additional wavelengths, it requires the kind of patient, systematic investigation that takes years rather than months. What it definitely represents, at minimum, is evidence that the process of stellar disappearance is not as simple as the two-sentence summary of failed supernovae might suggest. There is something happening in at least some of these locations that the current data is not sufficient to fully characterize. And every few months, when Rubin returns to the same patches of sky and compares new images to old ones, the candidate list gets a little longer and the pattern gets a little more defined. This is worth explaining in terms of what it means for our broader picture of the universe, because it is easy to hear a story like this and treat it as an abstract curiosity sitting at the far edge of cosmology. Interesting, but remote. That instinct underestimates how connected this question actually is to things that are considerably more immediate. The rate at which massive stars end their lives shapes the chemical composition of galaxies. Supernovae are the primary mechanism by which elements heavier than iron are dispersed through interstellar space, seeding the gas clouds that eventually collapse into new star systems, including the one that produced our own sun and everything in it, including every atom in every person watching this video. If a meaningful fraction of massive stars are bypassing the supernova stage entirely and collapsing silently into black holes, then the amount of heavy element enrichment happening in the universe at any given time may be different from what the models have assumed. The composition of future star systems forming right now in distant galaxies may be shaped in ways that existing chemistry models are not fully accounting for. That is not a crisis, it is not a reason to rewrite everything. It is, however, a reason to keep watching and to keep asking what is actually happening at the far edge of what our instruments can see. Here is what this story actually adds up to, stripped of the technical detail. We built an instrument capable of giving the sky a memory, and the first thing that memory revealed, among many other things, is that stars are disappearing in the dark more often than we expected, in more ways than the models cleanly predicted, in ways that are raising questions about how many silent black holes are scattered across a universe we thought we were beginning to understand fairly well. Every few nights, Rubin returns to the same patches of sky and adds another data point. Almost every time it does, something new shows up in the candidate list that did not exist in the previous run. The list grows, the pattern sharpens slightly, and the questions it is generating are not the kind that get answered quickly. This is what the leading edge of real discovery actually looks like. Not a clean announcement, with a tidy explanation attached, a persistent, growing body of observations that do not fit entirely within existing frameworks, being studied carefully by researchers who are honest about what they know and honest about what they do not. Rubin has been running its full survey for less than a year. It has 9 more years to go. Whatever it finds in year 3, in year 5, in year 9, the foundation of this particular mystery was laid in the first months of observation, when the system began returning images of places where stars used to be and no longer are. If stories grounded in what is actually happening at the frontier of real science rather than in what makes the cleanest headline are what you want more of, subscribe to this channel and turn on notifications, because Rubin is going to keep watching those patches of sky. And every time it returns something that does not fit, this channel will be here to explain it without the exaggeration. Drop a comment and tell me which part of this story landed hardest for you. And if you want to go deeper into the observatory that is catching all of this in real time, there is another video right now that covers everything Rubin has already found in its first year of operation. You should watch it next.